Dear students, welcome back to Akadimos Online. Today, our guest lecturer Noor Haq is here to discuss elaborately about the order of different bond lengths with multiple examples. He takes the helps of different resonating structure and hybridization and electronegativity of atoms forming the bonds. So, we must say another thing that the infrared spectrum data give idea about bond lengths that ratify the theoretical concepts used by our teacher to explain. So let's go ahead.
Dear students, today I am going to discuss a part of chemical bonding. That is the most important part I am going to discuss with you. That is, I will compare some bond lengths as well as some bond angles with the help of VACPR theory, concept of electronegativity, resonance. I will apply here. And the examples are highly important with respect to any competitive exam. First, I am going to discuss some bond length. In different competitive exam, there are questions. Their question already came, will come. That is, compare the bond length or compare the bond order. Bond order means number of bond. That is inversely related with bond length. Lower the bond length, higher is the bond order. And in that part, I will give some important example. And you may get common in different competitive exam. See my example. I will apply here VACPR theory, resonance as well as electronegativity. If compare the bond length, different bond length, compare the bond length. First, I am taking the example CO2, CO3 2 minus, that is carbonate, CO carbon monoxide, and CO plus, it is a radical. Here to compare the carbon oxygen bond length. Then how you will do compare it? You have to know here the structure of the different species or molecule. I am drawing. Carbon dioxide, the structure is this one. Here the carbon oxygen bond order is 2. Remember it. Carbonate radical. I am drawing the carbonate radical structure. C double bond O and 2 oxygen with -1 charge. And if I take resonance, there you will get 3 equivalent canonical form. And here is a pi bond, that pi bond equally distributed along the 3 sides of oxygen. Sigma bond is common, that means sigma fixed, and that 1 pi bond equally distributed among 3 oxygen. That is, for each oxygen, that is 1/3. Here the bond order. You can draw the different canonical form. There you will get 3 different canonical form. The CO structure I have discussed in chemical bonding part. CO structure, that is oxygen with plus formal charge and carbon with minus formal charge, and there is a triple bond and bond order 3. And now CO plus. CO plus, you have to remove an electron from CO, that electron of course from C minus, that since C minus is electropositive, you can easily withdraw electron from carbon. See here bond order also 3. Now by taking the bond order, maximum bond order CO and CO plus, that means minimum bond length, this 2, and then CO2 and minimum bond order CO3 2 minus, maximum bond length. Now the confusion will arise between CO and CO plus. Here see, in CO plus carbon is neutral. Neutral means electronegative than C minus. If minus will come, then electronegativity decreases, electropositivity increases. Since it is more electronegative than this, it will try to attract more electron cloud towards its nucleus more than C minus. That's why its bond length becomes shorter. Then I can draw the increasing order of bond length. Minimum CO plus bond order 3 with carbon neutral. Then increases bond length CO, both are 3 bond order. Then it will come CO2 bond order 2. Then comes CO3 2 minus bond order minimum 1 by 3. That means you got carbon oxygen bond length increasing order. Now I will go to give another example. See this, everything is clear. I have drawn here order of bond length with the help of bond order, and as well as I have considered here difference of electronegativity. Number 2, NO, nitric oxide, you know, NO plus, it is a radical. NO2, nitrogen dioxide, brown color. NO2 plus, nitrite radical, NO2 minus, and take NO3 minus. Here compare NO bond length and bond order, reverse order you will get. If bond length order increasing, then automatically bond order decreasing you will get. Here also you have to draw the structure of different nitrogenous species or molecule. First I am drawing NO. You know the structure of NO, that is this one, NO, here bond order 2. NO plus structure you know, here bond order 3. Now NO2, you know, oxygen minus and nitrogen plus with an odd electron. Here also you have to consider resonance. One sigma is fixed, pi equally distributed among the 2 oxygen. So here bond order 1 by 2, or you can say 1.5. Now NO2 plus, the structure is N, this is here bond order 2. Now NO2 minus structure is this one, plus of nitrogen removed by accepting electron. Here also 1.5 by taking another canonical form to average of the pi bond. And NO3 minus, you know the structure is O minus nitrogen plus, and this is double bond. Here also the 1 pi bond equally distributed among the 3 nitrogen, that is 1 sigma fixed, 1 by 3. Now I have drawn all structures. Maximum bond order NO plus, the minimum bond length NO plus. Then 2, you got in NO2 bond order NO2 plus also bond order 2, but their bond lengths are different. How do you compare? See, here nitrogen is neutral, but here nitrogen is plus charge. You know nitrogen with plus charge much more electronegative than neutral nitrogen. That's why its length shorter than NO, right? NO2 plus shorter than neutral NO molecule. You got bond order 2. Now I will go bond order 1.5. There are 2 species with bond order 1.5. Here also see, in NO2 there are nitrogen with plus formal charge, but here nitrogen is neutral. Nitrogen plus more electronegative, length will be the shorter. That means NO2 and less than NO2 minus. Next go NO3 minus, here bond order 1 by 3, least bond order, maximum NO bond length. And finally, you got idea how do you compare the different bond length. Here I have considered the bond order and electronegativity. Now I am going to give the third example where I will do compare bond length. Third example, take SO3, sulfur trioxide, you know that is the anhydride of H2SO4. SO2, anhydride of H2SO3. Take sulfite radical SO3 2 minus, and sulfate radical, very common, SO4 2 minus. I'll do compare here. Sulfur oxygen bond length. Sulfur oxygen bond length. To draw the sulfur oxygen bond length, you have to draw the structure of the different molecule and species. See, sulfur trioxide, there are 3 double bond with oxygen. This is SO3, and you know the structure of SO2, S double bond O, S double bond O, there you will get lone pair on sulfur. And SO3 2 minus, you know the structure, 1 double bond O, 2 oxygen with minus 1 charge, and you will get lone pair on sulfur. And SO4 2 minus, 2 double bond O and 2 with minus 1. Now, I will draw the bond order between sulfur and oxygen. Here, clearly seen it is 2. Here also it is 2. There are 2 number of bonds. Here see, sigma is fixed, I told you. This pi bond equally distributed among the 3 oxygen. That means it is 1 by 3. Here, see, sigma are fixed, 2 pi bond equally distributed among 4 oxygen. That means 1 2 by 4. Or you can say 1 by 2. Now I draw the bond length. See, the maximum bond order in SO3 and SO2. Here equal. If equal, then how do you will compare? You know the oxidation number of sulfur here, +6 or oxidation state. Here oxidation state +4. You know +6 oxidation state more electronegative than +4. That's why due to more electronegativity, here S double bond O oxygen, S oxygen, sulfur oxygen bond length slightly shorter than sulfur oxygen bond length in SO2. Now to compare minimum, then SO3 due to +6 oxidation state. Then SO2 +4 oxidation state, although both have equal bond order. Now, this is very clear to you. 1 by 3 less than 1 by 2. That means SO4 2 minus, and then least bond order, highest bond length SO3 2 minus. A very clean idea that you got the sulfur oxygen bond length. Bond order is the reverse order. Fourth example, take ClO2. This is chlorine dioxide. Take O minus hypochlorite, ClO2 minus chlorite, ClO3 minus chlorate, ClO4 minus perchlorate. See, here also, before go to the bond length, you have to draw their structure. You have to know the structure. ClO2 structure is very simple. 2 number of double bonds with 2 oxygen. Here a lone pair, also you will get an odd electron. This is ClO2. And its bond order is very clean. 2. No question of different canonical form. Here ClO minus, very clean structure, bond order perfectly 1. And ClO2 minus, the structure is this one. And here you will get a 2 lone pair of electron. Here see the bond order, 1 pi bond equally distributed among the 2 oxygen. If you draw the different canonical form, here bond order 1 by 2. ClO3 minus, this is double bond O, 1 is O minus, and here you will get 1 lone pair. And here C, 2 number of pi bond equally distributed among 3 oxygen, 1 2 by 3. And the last one, ClO4 minus, 3 double bond with 3 oxygen, 1 is O minus. Here C, 3 number of pi bond equally distributed among 4 oxygen atoms. Here the bond order 1 3 by 4. Now, from clean idea, directly you will get bond length from the bond order. Maximum bond order ClO2, minimum bond length ClO2. then ClO4 minus perchlorate, then chlorate ClO3 minus, then increases ClO2 minus 1 by 2 and perfectly one maximum bond length hypochlorite. You got idea about ClO bond length, a very clean example, important example from which you got chlorine oxygen bond length order. Dear students, similarly I am going to give the fifth example, which is also important. The example of compare, how do you will compare the bond length. The fifth example I am taking, silicate, very common species, silicate, zeolite, SiO4, 4 minus. Here I will take silicon oxygen bond length, then phosphate, I will take phosphorus oxygen bond length. That means I will do compare the bond length between SiO and PO. Then I will take SO4 2 minus sulfate, that structure already I have discussed. And the last one I will take ClO4 minus 1. That means here I will do compare the bond length between SiO with PO with SO and with chlorine O, ClO. How do you compare? Similarly, here you have to know the structure of the different species. The structure, if I draw, silicate SiO4 4 minus. This is the structure of silicate. And all silicon oxygen bond length, bond order is 1. Here silicon oxygen bond order is 1. Only sigma is present here. Now draw the structure of phosphate. 1 double bond O and other 3 single bond with O minus equivalent to halogen, valency 1. Now here the bond order C, this pi bond equally distributed among the 4 oxygen atom. That means here you will get 4 different canonical form. And if this pi bond equally distributed among the 4 oxygen, then its bond order 1 sigma is fixed, and this you will get 1 by 4. SO4 2 minus I have already discussed. The structure is this one. Again I am drawing it, and here 2 pi bond equally distributed among 4 oxygen, 1 2 by 4, and ClO4 minus also I have discussed. That is 3 oxygen with minus 1 charge, and here 1 pi bond ClO4 minus, there are 3 double bond with oxygen, 1 oxygen with minus, and 3 pi bond equally distributed among the 4 oxygen. That's why 1 3 by 4. See the bond order. Maximum bond order 1 3 by 4, then 1 2 by 4, then 1 1 by 4, then 1. Although their central atoms are different, but there are no contradiction. Here the highest bond order, minimum bond length. If you take the electronegativity, then chlorine here most electronegative also reduces the bond length. That means here no contradiction with bond order and electronegativity. Maximum bond order and maximum electronegativity, minimum bond length. Very clean picture of bond length. SiO maximum, then PO, then SO, then ClO. You got idea about the bond length or bond order of this example. Now I am going to give another important example, which is not exactly you can draw the order from the bond order. Let, very simple, H2O2. It is hydrogen peroxide. Another is F2O2. I'll do compare oxygen-oxygen bond length. Oxygen-oxygen bond length. See the structure of H2O2. This is H2O2. I'll do compare this one. And F2O2 structure is this one. Now see, both bond order 1. But their bond lengths are different. How do you will compare it? If I take the simple thought, hydrogen electropositive, but fluorine is electronegative. Fluorine withdrawing electron from this oxygen, which will make more electronegative oxygen. This fluorine will make more electronegative oxygen. That means This fluorine increases the electronegativity of oxygen. It will increases the formal charge del plus. Electronegativity if increases, then this bond length reduces. That means oxygen bond length in F2O2 less than H2O2. Similar example, let ethane CC bond length, if I do compare, and take hexafluoroethane. If I do compare the CC bond length, see, due to fluorine, which is withdrawing group, and that will increases the effective charge on carbon. That means this fluorine will increases the electronegativity of this carbon. Since electronegativity increases, bond length reduces. Here also CC bond length in C2F6 less than C2H6. Eighth example. Let it is CH3, CH2, CH2, CH3. I'll do compare this length. Let it is X. Taking another one, CH2 double bond CH single bond CH double bond CH2. This let it is Y. Take this one, triple bond C triple bond CH. This is Z. Now to compare. All are single bond. Apparently bond order is one, but their bond lengths are different. How do you will compare? I'll take here hybridization concept. You know this are sp3. These two are sp2 and these two are sp. And you know, with increase of S character, electronegativity increases. Since you know, S is the closest subcell in a particular cell. Close means more electronegative. That means sp more electronegative, electronegativity decreases, electronegativity again decreases. Another concept you know, I have discussed in fundamental concept of hybridization. Their major lobe size in sp maximum and minimum major lobe size in sp3. Overlap integral here maximum, here overlap integral minimum. If overlap integral increases, bond length reduces. Then bond length Z minimum, then Y and X is maximum. This is the increasing order of bond length. Here I have discussed by taking the overlap integral, major lobe size, or you can explain with the help of electronegativity with increase of S character, different S character. Thank you, student. Another application part of chemical bonding, that is I will do compare bond angle by taking VSEPR concept and electronegativity in the next class. Stay with us.